This problem is from chapter 22, number 3, about the pellets. And it reads, 2 pellets, each with a charge of 1 microcoulomb, which is 1 times 10 to the negative 6 coulombs, are located 3 centimeters, which is 0.03 meters apart. Show that the electric force between them is 10 newtons. There's a little bit more to it, but I'll read that out later. This is sufficient for now. So basically we have 2 pellets, and each of them has a charge of 10 to the negative 6 coulombs. And they're a distance of 0.03 meters apart, and we're supposed to figure out what the force is, of course according to Coulomb's law. So Fc equals K times Q1 Q2 divided by D squared. And I will show that in a moment on the calculator, but I figured the other thing I can do is show you this in an animation. Okay, so here there's a pellet. Pretty much I'm just going to make a circle there. There you go. It doesn't really matter how big it is. And if you read the numbers down below, you can see that at this point there are 0.03 meters apart. I also have to edit a few numbers here. It's supposed to be 10 to the negative 6. So that's what I'm doing, and then the other one also 10 to the negative 6. Notice that I'm not touching the mass here, because the mass doesn't matter as far as the electrostatic force is concerned. Okay, that's good enough for this one. At this point here, when I open this software, by default gravity is turned on as being vertical. I want to turn it off here because otherwise my pellets is just going to fall down. But then I also have to turn on electrostatics. So there it is, and you can see here is that Coulomb constant K, 8.99 times 10 to the 9th. Notice that our book is using 9 times 10 to the 9th, so they're using a rounded number because that 8.99 is really close to 9.0. So let's just use the book's number. It's only off by like 0.1%. Okay. Here for this one I'm gonna, let's see, measure the electrostatic force. There it is. I just need the total force. There we go. And then I hit the run button, and let's see what happens. And the two actually fly apart, and we see what happens to the force. It reduces the further they get away. However, they're just saying that these 2 pellets are 3 centimeters apart from each other, and so by them flying away I cannot fix this number here. So what I do instead is I anchor them down. Looks a bit weird, but actually this software does use an anchor for anchoring down. And then I hit the run button, and indeed it tells me that there is an electrostatic force between the 2 of 10 newtons. It doesn't specify in the problem if each of them is supposed to be positive or negative. Actually it does. It says each of them is charged of 1 microcoulomb, which implies that each of them is positively charged, so they are supposed to repel each other. Okay, and they do so with 10 newtons, and if I did the force on the other one it would be also 10 newtons. Okay, here is the calculation, and it will be K times Q1 times Q2 divided by D squared, so 9 times, and I have to be able to reach my keypad here. Hold on just a moment. Okay, that's better for me. I can also move this up a little bit more. There we go. Okay, so 9 times 10 to the 9th, and that's, oops, negative 9. No, 9th, that's right, 9th, times 1 times 10 to the negative 6 times 1 times 10 to the negative 6 divide by, and this one I would put in parentheses, 0.03. Actually, I didn't have to put it in parentheses. Take that back. Squared meters, and hit enter, and I come up with exactly 10 newtons. So this is what I just did. Fc equals 9 times 10 to the 9th times 10 to the negative 6 coulombs times 1 times 10 to the negative 6 coulombs. And then I try a fraction bar. Oh, that's not too bad. 0.03 meters. That's why I wanted to put it on parentheses on the calculator, because of the unit, but of course on the calculator I don't need a unit. Equals, and I come up with 10 newtons if I wouldn't have forgotten the unit for K, which is given early in relatively early in the chapter. There it is, introduce it, which is newtons square meters per Coulomb meters. And then the Coulomb square here divides with the coulombs here, and the meter square here divides with the meter square here, and that leaves, as shown, 10, and the unit is newtons. Okay, as far as the mass is concerned, for that I would have to say, okay, the force in the Earth's gravitational field would simply be the weight, mass times gravity, and since often we can use 10 meters per second squared for the acceleration due to gravity, then we can come up here with 1 kilogram, and that would be the equivalent mass that would experience the same kind of force of 10 newtons as its weight, and that would be like a heavy book, I guess. The 0.03 centimeters on the other one here, well, they are about an inch apart, and they have a very small charge on them, 1 microcoulomb. It produces the same force as the weight of this relatively heavy book, and that kind of tells us that the electrostatic force is indeed pretty large. The next problem is from chapter 22, number 4, which says electronic types. And it says, electronic types neglect the force of gravity on electrons. To see why, compute the force of Earth's gravity on an electron and compare it with the force exerted on the electron by an electric field of magnitude 10,000 volts per meter, which in parentheses is said to be a relatively small field. The mass and charge of an electron are given on the inside back cover. Okay, so here is a gravitational force in the Earth's gravitational field, and that's Fg equals G times the mass of the electron times the mass of Earth, because it's in Earth's gravitational field, the circle with a plus inside, that's the symbol for Earth, divide by the distance squared, which in this case in the Earth's gravitational field would be on the surface of the Earth, and so we could say d squared, or the radius squared of the Earth. And that equals then the gravitational constant given as 6.67 times 10 to negative 11, and really weird units, newtons times meter squared divided by kilograms squared times, and at this point I'm running out of space, so I'm going to push this all over here. There we go. Times, and the electron mass is given as 9.1 times 10 to the negative 31 kilograms, times the mass of the Earth is also given as 5.98 times 10 to the 24 kilograms, I believe in our book it's actually given as 6 times 10 to the... No, it is 5.98 10 to the 20 for kilograms, so it's not even rounded in our books. And then a fraction bar that actually came out pretty good, divided by the radius of the Earth, which is 6.37 times 10 to the 6 meters. And I just want to confirm that that is given in the book as well. Where did I get that from? Somewhere in the book. Oh yeah, there, I found it. 6.37 10 to the 6. I did find it in our book. Meters, which is 6,370 kilometers, or almost exactly 4,000 miles, and that needs to be squared, and that equals, and then I go to the graphing calculator, and I'm going to type that in just the way I got it here, 6.67. And if you happen to have a calculator that allows you to do this, there's, see this double E here, or it might just be a single E. You may click that, and then negative 11, which is 6.67 times 10 to the negative 11, times 9.1, again I'm going to do this here, E negative 31, times 5.98 E 24. So using this E or using 10 to the power, either one of them is the same, but you have to do it properly. Divide by parentheses 6.37. This time I do put parentheses because I'm using scientific notation, and it just makes it easier for the calculator to recognize that properly, that the square goes to both the 6.37 as well as the 10 to the 6th. That would be really important if I wrote here 10 to the 6th times 10 to the 6th. Then I really would need to put parentheses around it. In any case, I hit the enter button, and if I did everything right, that is the correct answer, 8.9 times 10 to the negative 30. So 8.9 times 10 to the negative 30, and the units would have to be newtons, square meters, and kilograms squared will cancel. Could have been a little bit quicker if I just had determined the weight of that electron. Mass E times acceleration due to gravity would have been 9.1 times 10 to the negative 31 kilograms times 9.8 meters per second squared. And if I do that on the calculator, 0.1 E negative 31 times 9.8 comes indeed out to 8.9 times 10 to the negative 30. But there also was a reasoning why I showed you this long one here with the gravitational law from a previous chapter, and the unit is here newtons, because we will use it in another problem relatively soon. Okay, for the electrostatic force, in this case here, notice that they don't give us a distance to the other charge. They don't give us the other charge. Instead, they give us the electric field. So we have to use a different equation than the Coulomb law that we used a moment ago, because we don't have another point charge here. So we're going to do F equals electric field times the given charge, and the electric field is given as 10,000 volts per meter, and the charge would be the charge of the electron, which is what we look up, 1.602 times 10 to the negative 19 coulombs, and all I really have to do here is shift the decimal point, so 1.6 times 10 to the negative 15, and then it would be volt coulomb per meters, but we can abbreviate that to newtons because that's what the unit for the force should be. This one here, and notice that negative 19 became negative 15 because I have to shift it 4 times here, 1 for each of those zeros. And then we can compare these two numbers. This one here looks really tiny. It is really tiny, but this one here looks much, much smaller, by 10 to the 15 times smaller. This is from chapter 22, problem 5, which reads, Atomic physicists ignore the effect of gravity within an atom. To see why, calculate and compare the gravitational electrical force between an electron and a proton separated by 10 to the negative 10 meters. The charges and masses are given on the inside back cover. So, to just make hopefully a quick drawing, here maybe a proton. There we go. Okay, it wasn't supposed to be empty, so I'm just going to make it filled here, hopefully. There we go. Okay, and now I'm going to make an electron, and maybe I'll make it green, filled. There we go, and here it is. And each one of them has a certain charge. In fact, the proton has a charge of 1.6 times 10 to the negative 19 coulombs. And I forgot one little thing there. Charge of the proton equals plus 1.6 times 10 to the negative 19 coulombs, and the charge of the electron is negative 1.6 times to the negative 19 coulombs. And the mass of the proton is what I look up in the back of the book. I want to say 1.67 times 10 to the negative 20. Yep. 1.67 times 10 to the negative 27 kilograms. Here I don't need a plus or a minus because masses are always positive, and then the mass of the electron is 9.1 times 10 to the negative 31 kilograms, roughly 2,000 times smaller than that of the proton. Okay, these two masses here, because of their mass, they attract each other gravitationally, so we have a gravitational force between the two, which is attractive. And of course it's the same either way, because the law says that gravitationally I have Fg equals gravitational constant mass of the proton times mass of the electron divided by the distance between the two squared, and that distance is given in the book as 10 to the negative 10 meters. So D equals, what is that, 1.1 billionth of a meter. There we go. So 1 times 10 to the negative 10 meters is the distance. So there's a gravitational force between the two, and as I said, it's the same for either one of them, because this can be turned around here, so both of them experience the same force. That's also in accordance with Newton's third law, the action-reaction principle. Of course, it's the electron that experiences a larger acceleration because of its much smaller mass. Okay, they're saying that, well, we have to compare this with the electric force. I'm just going to write there Fg, and the electric force is the Coulomb force between the two. So Fc equals K times Q1 times Q2 divided by D squared. There we go. And therefore we're going to have a Q1, an Fc, and they say that in the problem here that they imply, or let us show, asking us to show that the electrical force between the electron and the proton is much larger than it is for gravity, and so I make that error larger. It's not to scale, it's actually so much larger that I wouldn't be able to put it on paper here. In this case here, it's attractive because there are of opposite charges. The force still is the same. The Coulomb force is the same for either one of them, because again I could turn these around, and because of the action-reaction principle. And again, the acceleration between the two is the acceleration between the two is larger for the electron because it has a much smaller mass. Okay, if this was the attraction here, then the electron would just fly into the proton. But so to say, take this with a salt of grain or grain of salt. The electron, so to say, is orbiting, so it has a forward momentum here, relatively large one, and the force here is, oops, I didn't mean to draw this here. The force here is a deviation from going forward here in its momentum, and therefore it will get into an orbit around a proton, so to say. There is more to it when it gets to that level, but we have enough information to do the calculations, so I'm gonna plug in the numbers. Okay, I actually could go, well, I could go back a few times, but I'm just going to start it over. So 9 E9, or as I showed earlier, 9 times 10 to the 9th, times, and this one here would be 1.6 10 to the negative 19. And because it's the same for either one of them, for the electron, the proton, I can put that also in parentheses and square it. This only works for the Coulomb force because in this case, oops, in this case both charges are the same, and then I divide that by the distance of 1 times 10 to the negative 10 meters squared, and I come up with 2.3 times 10 to the negative 8th, so 2.3 times 10 to the negative 8, and the units are newtons. And then I do the same for the gravitational law, so it's going to be 6.67 10 to the negative 11 times the mass of the proton, 1.67 10 to the negative 27 times the mass of the electron, 9.1 times 10 to the negative 31, and at this point you can already see that it's going to be much smaller because I'm comparing negative 31 and negative 27 to the negative 19 twice here, and those numbers are quite a bit smaller, and the gravitational constant is much smaller than the Coulomb constant. Okay, anyway, divide by 1 10 to the negative 10 meters squared, and I come up with 1 times, or 1.0 I believe, times 10 to the negative 47 newtons for the gravitational force. And we can see that the electric force is 39 orders of magnitude larger, 10 to the 39, so 1 with 39 zeros, and I came up with that by comparing negative 8 to negative 47. So if you write out this number, it would be a 1 with 39 zeros behind it. That's how much larger the Coulomb force is than the gravitational force, and that justifies that the gravitational force between the proton and the electron can be readily neglected compared to the electrostatic attraction. Okay, here I made a little animation, proton and electron, and let me show you. So here's the electron, 9.1 times 10 to the negative 31 kilograms, and here it's charged, negative 1.6 10 to the negative 19 coulombs. Notice that the electron at this point here doesn't have any velocity, so I'm going to keep that 0, which means that there's really, the electron is not going to orbit here. The proton I just anchored down, so it's not going to go off the screen. It may do very slightly move. Anyway, here's the mass of the proton, 1.67 10 to the negative 27 kilograms, and the charge, positive 1.6 10 to the negative 19 coulombs. And the way I start this out with is that I turned electrostatics off, okay, and I turned gravity on in such a way that they're not going to fall down, but that they attract towards each other. It would be called planetary, except it doesn't have a speed to begin with, so they're really slamming into each other. Okay. One of the things I have to do in my animation is the accuracy, and that means, for example, here I tell it, give me one diagram every 120 seconds, so calculate it every 20 minutes, so it's relatively slow what the electron is doing. It needs a lot of time in order to do something. So here it's just a gravitational attraction between the two. I hit the run button, and this would be here after 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes, 12 minutes, 14, 16, 18, 20 minutes, 22, 24, 26, 28, half an hour, 32, 34, 36, 38, and so on. So you can see that this tiny distance, which is written, by the way, down here, 1 times 10 to the negative 10 meters, it takes half an hour just to get to half distance of the proton at a billionth of a meter. Okay, anyway, in respect to that, I'm going to get to electrostatics in just a moment, but I need to drastically, before I do that, I need to drastically change the timing here, and I'm going to change it in such a way, this is the number I remembered, let's see, 19, and then when I click somewhere else here, so here what I'm going to show is one image every 10 to the negative 19 seconds. So it's really fast, the time here, really fast. You get an image every gazillionth of a second, okay? And I still have it on gravity, and notice that one diagram after another, you're not going to see anything. I mean, this would take you forever, and I mean in the neighborhood of eternity, to actually get to half an hour, because I made the time here so fast, 10 to the negative 19 seconds, that it needs to add up a lot of diagrams in order to actually get to half an hour where we actually can see what happens to the electron. So gravitational attraction between these two here is very small. Okay, let me reset it, and let's go over to turning gravity off, turning electrostatics on. There we go. And double checking the accuracy, so it's just as fast. There we go. And now I hit the run button, and notice under electrostatics it moves very fast within this gazillionth of a second, which tells us that the electrostatic attraction is much larger than the gravitational attraction. For the gravitational attraction, I need to be in the neighborhood of 10, 20, 30 minutes in order to actually see something. Here it's a gazillionth of a second, and we already see quite some attraction here electrostatically. If this is all that would happen, then the electron would just slam into the proton. That's not the case. So I'm going to give the electron a certain initial speed, which I calculated on the side as being, or so I thought I had it written down. Oh yeah, on my calculator, as 1.59 times 10 to the 6 meters per second, roughly 1,590 kilometers per second, or roughly 1,000 miles per second. And of course, it has only a very small radius, so within 1 second it makes billions of orbits. And again, I have the time here really fast, so at a really small number, and when I hit the run button you can see the electron orbiting nicely. My time here is so fast, that means at such a small time difference from one diagram to the next that we actually can see it orbit around. Just like a planetary orbit, except this one here is due to electrical attraction. Notice earlier I turned off gravitational attraction. So this whole thing here was just the animation connected to the problem that I discussed of comparing the gravitational to the electrostatic force. This problem is from chapter 22, number 10, and I figured as I'm going to read it, I actually picked up this animation, so I'm just going to play this animation. And you can read through it. It actually doesn't have any voiceover except mine that you hear right now. And I'm just going to read the problem from the book, which more or less goes along with what you're seeing here. So you hear it slightly different than the way you see it. The problem in the book is, in 1909, Robert Millikan was the first to find the charge of an electron in his now famous oil drop experiment. In that experiment, tiny oil drops were sprayed into a uniform electric field between a horizontal pair of oppositely charged plates. The drops were observed with a magnifying eyepiece, and the electric field was adjusted so that the upward force on some negatively charged oil drops was just sufficient to balance the downward force of gravity. And that's kind of what you see here in this animation. From left to right, by the way, you do see X-rays coming out, which is charging the oil drops. Here is a question: why did Millikan select only oil drops for his experiment? And I quite couldn't understand that little diagram they showed there. Why not water? It turns out, I looked it up, it says the oil was of type usually used or was chosen because it had an extremely low vapor pressure. Ordinary oil would evaporate under the heat of the light source, causing the mass of the oil drop to change over the course of the experiment. That's also why water or any other liquid was chosen, because it would just evaporate too quickly under the heat of the light source. They needed to be a light source because this was visually observed, so somebody would sit there with a microscope and actually observe the droplets drifting. So it goes on in the book's problem, that is when suspended upward force QE, there's the electric force, just equaled mg, the downward gravitational force. Millikan accurately measured the charges on many oil drops and found the values to be whole number multiples of 1.6 times 10 to the negative 19 coulombs, the charge of the electron. For this he won the Nobel Prize. I believe he was the second US American to win the Nobel Prize in, I want to say 1912, 1920, somewhere around there. Overall, I did the experiment myself when I was in college, and it's a relatively boring experiment and tedious too, because you just have to sit there and you have to watch that oil drop floating and measure as you go along. In any case, let's do the calculations the way they ask us to do them. So if a drop of mass 1.1 times 10 to the negative 14 kilograms remains stationary in an electric field of 1.68 times 10 to the 5th newtons per coulomb, what is the charge of this drop? So it says problem A, and then they give that, they say, okay, here's an oil droplet, and it has a mass of 1.1 times 10 to the negative 14 kilograms, and as you saw, because of gravity it would fall down. But then there is an electric field E, so because of its own gravity mg it would fall down, but then there is an electric field just of magnitude 1.68 times 10 to the 5th newtons per coulomb, and it is adjusted in such a way that it pulls up the electron with Q times E, charge times the electric field. What is the charge of this drop? So this force over here is the same as this force over here, except one of them is negative and the other one positive, but in magnitude they're the same. So I said mg equals to Q times E, and they're asking for charge, so the charge equals mg divided by E. You can see the algebra. All I did was I took the E from here, put it to the other side, mg divided by E, and that equals Q. That's all I did. Okay, and then I plug in the numbers here. The mass 1.1 10 to the negative 14. The acceleration due to gravity, I'm going to use the 9.8 meters per second squared. Makes it a little bit more accurate than our typical 10 divided by the electric field of 1.68 times 10 to the 5th newtons. That's also because they give us 2 and 3 significant figures here, so I might as well use the acceleration due to gravity with 2 significant figures. And plug that in on the calculator. Let's see. There we go. Okay, just a little bit out of the picture. There it is. Almost there. 1.1 e negative 14 times 9.8 divided by 1.68 10 to the 5th. Okay, the way I just wrote this here, 1.68 e fifth works without parentheses. If you tried 1.65 times 10 to the, which is this little dash here, 5th power, you would have to put it in parentheses, because otherwise your calculator interprets it as a multiplication rather than a division, which is what it is. It's a division. Okay. Anyway, enter, and I come up with 6.4 times 10 to the negative 19. So 6.4 times 10 to the negative 19, and the units, they look really bad here. Kilograms, meters per second squared, and then times coulombs and divide by newtons, because I multiply with the reciprocal of this one here. So really bad units, but overall these are all standard units, and what should come up with is the standard unit for the charge, which is the Coulomb. So I'm just going to write Coulomb there. So that's the answer to the first part. Then there is part B that says, how many extra electrons are on this particular oil drop, given the presently known charge of the electron? Well, this one here, so I look up the charge of the electron, and it says 1.6 times 10 to the negative 19, and that kind of looks similar to the charge of the electron. So compare our answer 6.54 times 10 to the negative 19 to the electron charge of 1.6 times 10 to the negative 19 coulombs, and we can see that that number here is 4 times larger as this one, which means that there must be 4 electrons, extra electrons, sitting on the oil drop that are attracted upwards due to the electric field applied in this experiment, and that just is enough force to hold it up against the oil drop's own weight. If there had been fewer electrons, then this force here, this upward force, wouldn't be as large, and the oil drop actually would fall down with 3 or fewer electrons. If there had been more electrons, then this force here would be larger than the weight, and it would actually start drifting up. But the 4 electrons here makes it in such a way that this force here balances this force, just as it is written here.